This lesson's going to be a pretty superficial look at kinematics, where we're discussing position, velocity, and acceleration. So let's just go through the basics of kinematics. So when we're talking about position and displacement, we say that position of a particle moving in a straight line is determined by its distance from a fixed point O on the line called the origin, and whether it is to the left or the right of O. So conventionally, and it doesn't have to be this way, but conventionally the direction to the right of the origin is considered to be positive, and obviously to the left of it would be negative. Okay. So what we're doing in Year 12 methods and Year 11 methods is particles only move in a straight line. Okay, and if this is the origin here, the particle has moved x units to the right of the origin. Okay, if it's moved this way, it's moved to the left of the origin. Now what we can do let's just see where this goes. Consider a particle which starts at O and begins to move. The position of a particle P is determined by the number x. If the unit is meters and if x is equal to -3, then the position of P is 3 meters to the left of the origin. Okay, so that negative sign means it's on the left of the origin, whereas the positive sign means it's to the right of the origin. Now, the displacement is defined as the change in position of the particle, and sometimes we can develop a rule for that. So I've always used the example of me moving in a class, and just say I move to the front of the class, and all I do is I move in a straight line, left or right of the whiteboard. So I plant myself, like the origin is the middle of the whiteboard at the front of the class, and I either move to the left or the right. Now, what you might be able to do is notice that I move in exactly the same way every single day that I teach the class. And what you might consider doing is developing a rule, okay? Now, when you do that, what you might notice is that you would start to calculate my position with respect to time, okay? So in this case, my position is defined as a function of t, time. So hence, x of t, this thing here, x of t, is the displacement. So here we've got x, and this would be x of t is the displacement relative to the origin at time t. And essentially what happens to this x-axis here, this axis here, is we plonk it up there. That becomes the x-axis. Here's the origin, okay, and the particle moves left or right of the origin, and this axis now becomes t, which is time. That's why we say that the position of a particle can be modelled with respect to time, and you might find that that's what I do in class or something like that. Specification of a displacement function together with the physical idealization of a real situation constitutes a mathematical model of the situation. Okay, so yeah, it's Mr. Miller moving in class, or particle, blah blah blah. All right, so what's velocity? Okay, so we need to just make sure that when we talk about velocity, we don't put velocity or speed. Okay, they are very different things. Okay, so velocity is velocity and speed is speed, and they should never ever be used interchangeably. So the velocity of a particle is defined as the rate of change of its position with respect to time. Okay, both the average rate of change, the change in position over a period of time, and the instantaneous rate of change, which specifies the rate of change at any given time, can be considered. So there's two things that we can look at: the average rate of change in position over time as the velocity, so the average velocity, or the instantaneous range, which gives us the velocity at any given point in time. Right, so our average velocity, that should look familiar. That's just the gradient between points. And obviously, to get our instantaneous velocity, what we would do is derive it to get x dash t, which would be our velocity function, which is what that alludes to. Note that the difference between velocity and speed is it's the change in position relative to time, okay? And if we looked at a car driving around a circular track, all right, so car starts here, goes around in a circular track and comes back to the start. It might have taken the car 1 minute to drive the, I don't know how long, what could you do in a minute? Like a 4-kilometre course, okay, around the circle there, and that would generate a significant speed. The difference would be that if I was talking about velocity, remember, that's the change in position with respect to time. And notice that the particle or the car returns to the origin, returns to the starting point, okay? And so what we would actually say about this is that the velocity of the car is zero, okay? Because the position, the change in position with respect to time, basically after 1 minute, it hasn't changed position. It's exactly where it started, okay? Right, finally, what we have is acceleration. So acceleration of a particle is defined as the rate of change of its velocity with respect to time, okay? So average acceleration can be done by looking at the this function here. So what we do is we grab the average for the time interval of the velocity function. So we grab 2 points on the velocity function, work out the gradient, and that gives us the average acceleration. More likely, we're going to be asked for the instantaneous acceleration at a given point in time, which we would derive the velocity function and then bang in a value for x, which would give us the instantaneous acceleration, or we'd double derive the displacement function to get the acceleration function straight to it, and then bang in a value of x, which would do the same thing. Now note that last year what we did was we went from position to velocity to acceleration. Now that we know integration, we can actually return to those original functions as well. So we can go backwards from an acceleration function to a velocity function. All right, so note some units of measurement. 1 meter per second can be written as 1 meter per second. That is 1 meter over second, which could also be written as 1 meter second to the power of -1. Physics students do that more so than mathematics students. We usually use the centimeters per second, kilometers per hour. Okay, so the motion of a particle moving along a straight line is defined by this function here. Okay, so anytime you do kinematics questions, we really want to graph that function. So x of t equals t take 1. All right, so basically we've got an upright parabola, starts at the origin and has another intercept at 1. So it's going to look like this, where t is greater than or equal to 0. Okay, the average velocity of the particle in the first 3 seconds. All right, so here's second 1, second 2, second 3. So we would get it there. Now, a lot of people, what students do with this one is they find x dash t, and then they put in x of 3, x dash 3, x dash 0, which actually would be the average acceleration. Okay, no, it wouldn't be. I don't even know what that would give you. The average instantaneous rate. Ooh. Anyway, the average velocity, what we're going to do is note, we want the first 3 seconds. So we're going to go x of 3 take away x of 0. So average velocity, remember, is the change in position with respect to time. Okay, so we're going to work out the position change on average. And that's over 3. Okay, so when I put 3 in there, I've got 9. 9 take 3 is 6. Over 3 is equal to 2 meters per second. Meters, yeah, seconds. Okay, the distance travelled by the particle in the first 3 seconds. Always be careful. Okay, so how far has it gone? So what's happening here at the start is the particle is moving to the left of the origin. Okay, so it moves to the left of the origin, and at this point here what it does is the particle changes position and starts moving to the right of the origin, okay, or starts moving in the right direction. It's still left of origin, but it's moving to the right. Now it's right of the origin and moving right. And what it's going to do, this is not to scale, it's going to end up at point 3. Okay, so to do this, I need to do this in a couple of parts. The first thing I'll do is work out the distance from there to the turning point, okay, because that's how far it moves to the left of the origin, okay, so it moves all the way down to here. So I know that the two x-intercepts are 0 and 1, so to work out the turning point, I'm going to do x of a half, and that's going to be a quarter So a half times a half is a quarter. Take away t, take away a half, and that's going to be negative a quarter. Okay, so the turning point here is going to be half, comma, negative quarter. Okay, so the distance then is going to be the absolute value of the negative a quarter, which is going to be a quarter. So it's a quarter from there to there. It's another quarter from there to there. And then it's the distance from 0 up to whatever the y value is there. So it's going to be x of 3, which is 9. 9 take 3 is equal to 6. I think I worked that one out before. So that's a quarter plus a quarter, which is a half. A half plus 6 is 6.5 meters. All right, the average speed of the particle in the first 3 seconds. Okay, now remember the average velocity is the change in position with respect to time. The average speed is going to be, so speed equals distance over time. So that factors in the distance covered, okay? So again, I go for a jog from my house, I do this big loop, and I come back home. If my wife asked me what was your average velocity over that run, I would have to say, unfortunately, that my average velocity was 0 because the change in position with respect to time would be no change. I got back to where I started. Whereas if she said, what was your average speed? Okay, well, that's completely different, okay, because that factors in the distance I ran. If I ran 10 kilometers in 1 hour, okay, then I could calculate my speed. So over here, we're going to take the distance that we've written down here, which is 6.5, and we're going to divide that by the time that took, which is 3, which is 65 on 3, and that is going to be, again, meters per second. The velocity at time t seconds. So we want to get the velocity at any given time. So all that's going to be, so if my original function is x of t equals t squared, is it take t or plus t? Take t. So the velocity at time t seconds is going to be given by x dash t equals 2t take 1. The acceleration at time t seconds is either x double dash t or the derivative of x dash t. So the double dash will be the derivative of this, which is equal to 2. Constant acceleration. So here we go. A particle starts from rest 3 meters from a fixed point and moves in a straight line with an acceleration of this. Find its position. Okay, so basically we've got a particle starts from rest 3 meters from a fixed point and moves in a straight line. Now this starts from rest is an important thing to note, okay, because what it means when it says it starts from rest is that its velocity, so when t is equal to 0, its velocity will also be 0, okay? Now that's going to help us go backwards from our acceleration function to the velocity function. So to get that, what I'm going to do is, let's just say that we'll let a equal, let's call it a function, f of t. Okay, so a is equal to f of t. All right, so to get the velocity function, I'm going to say velocity is equal to 6t plus 8 dt, and that is going to be 3t squared plus 8t, and because at time 0 the velocity is 0, this is just going to be plus 0, or we don't really need to worry about it. Okay, so that's our velocity. Okay, didn't really need to define the function. In fact, that function definition, yeah, didn't work. Okay, so then what we would do is note that we want its position function. So that's its velocity function. We want to now get its position function. So to get its position function, what we're going to say is, let's call it P, position function, is equal to, or displacement function, D if you want, the 3t squared plus 8t dt is equal to t to the 3 plus 4t squared plus c. Okay, that's our position function. And I know that it starts from rest 3 meters from a fixed point. So at time 0, it's 3 meters from the fixed point or the origin. Now it's positive 3 as well, so I'm presuming that that's of note. Okay, so let's sub in that. So 3 is equal to c, therefore p is equal to t to the 3 plus 4t squared plus 3. Okay, and what you'll note then is that if I define f of x equals x cubed plus 4x squared plus 3, if I diff that f of x, I'm going to get my velocity function, and when I diff the velocity function, I'm of course going to get all the way back to the acceleration function. So you can move between the functions quite nicely when you get more information. So when the question actually gives you that further information, you'll know that you can actually write in full the antiderivative or the velocity and the position functions with that particular information. Okay, this last question that we'll do for integral calculus is a pretty good one here, 2013 exam 2. Okay, so what we've got a function here, root x take 1, and what we want to do is find this shaded area. Okay, and which one of the following definite integrals could be used? So notice that it's not asking us to actually do it. Okay, so look, these are good, these ones. This is how I wouldn't do this problem. So what we could actually do is just manually work out the area under the curve here, area of the box, do the subtraction to get the shaded area, okay? And that's going to be, what's that? That's like 5 and 1, that's 4 times. So the rectangle is going to be 4 times the height, which will be f of 5, which is 4 times 2 is equal to 8. So the rectangle is 8, and I could run the integral, which would be, where is integral? There you are. 5, 1, x take 1 all to the half dx, which is that, and then I do 8 take away 16 on 3 is 8 on 3. So the actual area is equal to 8 on 3 units squared, but actually this question is not asking us for that. Now I could manually go through and process then each one of these one by one to see which one will match it up. And certainly we can see that A is not correct. Okay, so that is going to give us the area under that curve there, not this curve here. Now between 2 and 0, why would I be going between 2 and 0 on the original function? How is that going to give us the same area? 2 and 0, don't think so. 5 and 0, 2 take away, not sure even why that's a thing. And over here we've got an x squared and an x squared here, and our function that we're trying to integrate is that one there. So how can these possibly be right? So you might think, oh yeah, that's our answer, but actually it's going to be one of these. All right, now how do I know? Well, what you want to think about, girls, as you look at this problem is I would actually think about tilting my head to the right. And what I would do is tilt 90 degrees to the right. And what you might notice there, girls, is that we've got a parabola. Okay, that actually is a parabola. And what I'm going to do, girls, is to show you that, just going to write this quickly as y equals root x take 1. And now what I'm going to do is inverse this. Okay, so I'm going to write it as y squared equals x take 1, y squared plus 1 equals x, y equals x squared plus 1. Okay, so what we would have here, and I know there's a plus or minus in here. Is there? No, there isn't. Right, what we would have here is that graph there. All right, so what would we do then? Now note that we would look for this area here. So this area here on the y-axis would be 0, 2. That's going to be up to 2. And, well, no, I've got -2 there. That would be 2 there. And what that would do is give us the full area here, including this bit here. Now notice that the picture doesn't want that part. Okay, it wants us to shave it off. So what we would do is have to go, all right, this one can't be right. We can't integrate between 2 and 0 to get it, okay, because that's going to give us this bit here. So what we would do is, well, how else could we get that area? And the answer is that I would just drop this down 1 unit. So I'd bring it down 1 unit, which would then give us the area that we wanted there. And that's actually what's happened with this function here, okay? So that one has basically given us too much area. We drop it down or subtract it by 1, and then it'll give us this area here, okay? So let's just try it out and see whether that does give us 18 on 3 as an answer. I know it will. 2, 0, x squared dx. And lo and behold, it's 8 on 3, okay? So, yeah, tough question, that one.